Picture the Milky Way, all hundreds of billions of stars, all 100,000 light years of spiral arms. Every sun you've ever seen in the night sky, every constellation, every world, every alien civilization that might exist somewhere in our galactic backyard. Now imagine taking that entire galaxy, everything in it, and shrinking it down until it fits inside something else. Something so catastrophically massive that our galaxy would drift through it like a speck of dust drifting through a cathedral. That thing is real. It has a name. It is called IC 1101. And when you truly grasp its scale, when you understand what it is and how it grew, you realize something disturbing. This object should not exist. The laws of galaxy formation, as we currently understand them, struggle to explain how anything could get this big. And yet, there it sits, silent, ancient, waiting. Before we go any further, if you find these deep dives into the biggest, strangest things in the cosmos fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let me start with something that will unsettle you a little. Right now, you are reading on a small rocky planet orbiting an ordinary yellow star in one of the outer spiral arms of a galaxy called the Milky Way. That galaxy contains somewhere between 100 billion and 400 billion stars. It stretches roughly 100,000 light years from end to end. If you could see it from the outside, it would look like an enormous spinning wheel of light, spanning a distance so vast that a beam of light traveling at 300,000 kilometers every second would take 1,000 centuries just to cross it once. That is the scale of home. That is everything you have ever known, everything human beings have ever seen with a telescope in our local neighborhood, everything the ancient astronomers ever wondered about when they looked up at the night sky. And now I want you to imagine picking up the entire Milky Way. Every star, every planet, every nebula, every black hole. Cup it in your hand like a marble, and then place that marble inside another galaxy. The galaxy you are placing it into is called IC 1101. And here is the part that starts to feel wrong. The Milky Way, our unfathomable island of stars, would drift inside IC 1101 like a grain of sand drifts through a swimming pool. You could fit our entire galaxy inside it, and then you could fit another Milky Way beside it, and another, and you would keep going until you had placed hundreds of galaxies like ours inside a single object, and there would still be room. The extended halo of IC 1101 stretches somewhere in the range of 2 to 4 million light years across in the most generous older measurements, with more recent and conservative studies favoring the lower end of that range or below. Its central stellar body, the tightly bound region where its stars are most densely concentrated, is estimated at somewhere between 400,000 and 600,000 light years wide. Either number is monstrous. Either number breaks the frame. And this is the moment where I need to be honest with you and say that these figures come with real scientific caveats. That the phrase, largest galaxy in the universe, gets thrown around too casually, and that the true story is more complicated and more interesting than a single superlative can capture. But before we get to those caveats, before we start drawing lines and asking what counts, I want you to sit with the raw scale of it for just a moment longer. Because the shock is not in the number. The shock is in what the number means. Let me try to make it tangible. If the Milky Way were a coin sitting flat on your kitchen table, IC 1101, using its wider halo estimate, would be roughly the size of a large dinner plate. Not slightly larger, substantially, catastrophically larger. Now, imagine standing inside that dinner plate galaxy on some hypothetical world. When you looked up at the night sky, you would not see anything resembling our sky. You would not see the familiar Milky Way arch overhead, like a hazy river of light. You would see something so much stranger and denser and older that human language does not really have the right words for it. You would be surrounded by trillions of stars. Yes, trillions with a T. Estimates of the total stellar population of IC 1101 in its most generous accounting hover around 100 trillion stars, though more conservative measurements come in significantly lower. Compare either figure to our galaxy's 200 to 400 billion. Even at the low end, we are talking about a galaxy with something like 10 to 50 times more stars than our own. And at the high end, the ratio climbs to hundreds. And the vast majority of them are old, red, dim, and packed into a smooth, roughly spheroidal structure without the neat spiral arms we're used to seeing in pictures of galaxies. It would feel less like standing under a sky and more like standing at the bottom of an ancient sea of firelight that stretched away in every direction for millions of years. Now, let me talk about where this thing actually is. Because part of what makes IC 1101 so strange is not just how enormous it is, but how far away it is, which tells us something profound about how long its light has been traveling to reach us, and about how long the galaxy itself has had to grow. IC 1101 sits at the heart of a galaxy cluster known as Able 2029. That cluster is roughly 1 billion light years from Earth. Sit with that number for a moment. 1 billion light years. The light you see when you look at IC 1101 tonight is light that left the surface of that galaxy over 1 billion years ago. That light began its journey long before there were dinosaurs, long before there were mammals, long before there was any complex animal life on our planet at all. When those photons started traveling toward us, Earth was populated almost entirely by single-celled organisms and the very earliest simple multicellular forms. There were no forests. There were no fish. There were no insects. The continents were arranged in configurations that no map today would recognize. And across the vast dark ocean of intergalactic space, a beam of light was leaving a supergiant elliptical galaxy on a 1 billion year journey to eventually strike a telescope on a planet that did not yet contain anyone capable of pointing a telescope. That is what you are looking at when you look at IC 1101. A snapshot of something impossibly large from a time that predates almost every complex organism that has ever existed on Earth. And here's the truly disorienting thing. IC 1101 is already ancient in that snapshot. It is not a young galaxy just starting to grow when that light left. It is already an old, red, evolved, massive supergiant that has been feeding for billions of years by the time those photons begin their voyage. Which means whatever this galaxy is doing now, we will not see for another billion years. We are always looking at its past. We are always looking at a version of it that has already been superseded by something even more absurd, sitting where it sits in the current cosmic era. Everything about this object plays out on timescales that make human history look like a single frame of a very long film. Let me back up and tell you a little about how we even came to know about IC 1101. Because the story of that discovery is itself a lesson in how our understanding of the universe has scaled up over the past 2 centuries. In 1790, the astronomer William Herschel, working in Britain, who had already spent much of his life systematically sweeping the sky and cataloguing everything he could find with his telescopes, spotted a faint smudge of light in the constellation of Serpens. He recorded it as one more nebulous object among the thousands he was collecting. At the time, nobody knew what a galaxy was. Nobody knew that the fuzzy blobs Herschel was writing down were island universes, each containing hundreds of billions of stars, sitting at incomprehensible distances from us. He was just diligently mapping the sky, marking down every faint patch of light he could see and noting its position. That faint smudge, that unassuming little blur, was eventually recatalogued in the index catalogue of nebulae and star clusters as the 1101st entry. The letters I and C in its name stand simply for index catalogue. The number is just a serial position on a list. This is the origin of its name. There is nothing grand about it. Nobody at the time realized that a boring administrative designation had just been assigned to what would eventually turn out to be one of the most massive gravitationally bound structures anyone had ever identified. It would take another century and a half of astronomy, of ever larger telescopes, of the invention of photography and spectroscopy, of the realization by Edwin Hubble and others in the 1920s that these fuzzy blobs were not clouds inside our own galaxy, but were themselves entire galaxies at vast distances, before anyone could begin to appreciate what Herschel had actually discovered. And even after that, it took decades more of careful measurement to figure out just how far away IC 1101 really was, how bright it really was in absolute terms, how much of the sky its diffuse outer regions actually covered. Every time astronomers took a longer exposure with a better instrument, they realized the galaxy extended a little further out than they thought. The faint outer envelope of stars just kept going, and going and going, fading gently into the background rather than ending in any clean edge. This is one of the reasons the largest galaxy claim needs so much care. Where do you say the galaxy stops? At what surface brightness do you draw the line? Different choices give you very different answers, and different papers over the decades have offered very different sizes, depending on the criteria used. If you count the tightly bound stellar body, the region where the stars are densely packed together and the light is bright, IC 1101 is roughly 600,000 light years across. That already makes it a giant. That already makes it about 6 times the diameter of the Milky Way. If you count the extended diffuse halo, the vast glowing envelope of stars that fade slowly into the intergalactic medium, some measurements push the number up to 2 million or even 4 million light years. That is where you get the truly staggering figures that have made this object famous. And here is the honest scientific point I want to make clearly. The largest measurements are the ones that depend on the fuzziest definitions. The stellar body itself is well established. The vast halo is real, but its exact extent depends on how deeply you can image it and what threshold you set. So when people say IC 1101 is the largest galaxy in the universe, they are usually citing the halo figure, and that citation is doing a lot of work. Other galaxies, when measured the same way with the same generous definition of edges, I could sometimes rival or approach it. There is a real debate in the astronomical community about which supergiant elliptical actually deserves the crown. And the crown itself is a slightly artificial construct that depends on where you draw the line. But here is why I do not want you to walk away from this feeling deflated, because even the conservative, tightly bound measurement makes IC 1101 one of the most extreme objects in the known universe. Even the smallest reasonable figure describes a galaxy that dwarfs our own by more than an order of magnitude in diameter, and by 2 full orders of magnitude in stellar content. Whether you take the low estimate or the high estimate, you are still describing something that has no analogue in our local cosmic neighborhood. There is nothing near us that looks like this. The largest galaxy in our local group, the collection of galaxies that includes the Milky Way and Andromeda and dozens of smaller companions, is Andromeda itself. It stretches roughly 220,000 light years across. That is a substantial galaxy. That is a genuinely massive object. And IC 1101 dwarfs Andromeda the same way it dwarfs us. Even our largest neighbor is small compared to this thing. Try to imagine for a moment standing outside the Milky Way at some vast distance and looking at our home galaxy hanging in the void. You would see a beautiful spiral, illuminated by hundreds of billions of stars, with dust lanes tracing the arms and a bright central bulge. It would take up a decent portion of your sky. It would feel enormous because it is. And now imagine the same viewpoint, but the Milky Way is gone and in its place is IC 1101. It would not just be bigger, it would swallow your field of view. Its diffuse halo alone would extend across a stretch of sky that would take you hours or days to scan if you turned your head. Its central body would glow with the light of trillions of ancient stars. And unlike the Milky Way, it would not have arms. It would not have that beautiful spiral structure. It would be a smooth, roughly egg-shaped, softly glowing mountain of stars, with a subtle brightness gradient from the intensely bright core out to the fading edges. It would look, in some ways, like a gigantic, quiet, ancient sun made of 100 trillion suns. Now imagine, instead of standing inside it, that you are approaching from outside. You are on a spacecraft traveling toward Able 2029 from some vast intergalactic distance. First, you would see the cluster itself, a swarm of hundreds of galaxies, distributed in a rough sphere 10 million light years across, glowing in the intergalactic dark. At this distance, most of the galaxies would look like faint fuzzy blobs, each one a Milky Way or larger, arranged in a slowly rotating cloud. But even from millions of light years away, one galaxy in that cluster would stand out. Not slightly, dramatically. There would be a single object at the center that dominates the field of view, brighter than everything around it, larger than everything around it, glowing at the gravitational bottom of the entire structure like a lantern at the center of a slow-moving fog. As you drew closer, the other galaxies would still remain visible, but they would begin to look like satellites, attendants, small companions orbiting a giant, and the giant would keep growing in your window, not because you were approaching faster, but because there was simply more of it. Its diffuse halo, invisible from far away, would begin to fill the space between the more distant cluster galaxies. Its central body would resolve from a bright point into a soft, symmetric, glowing ellipsoid. And by the time you were close enough to see the individual stars in its outer envelope, you would realize that the halo of this one galaxy alone extended further than the entire main body of the cluster you had been navigating through. Compare that to what an outside observer would see approaching the Milky Way. Our galaxy is a substantial object, a beautiful spiral, but the local group around it does not orbit us the way Able 2029's galaxies orbit its center. Andromeda is comparable in mass to the Milky Way. The local group has no clear king. Nothing dominates. It is a small, quiet, democratic neighborhood. What we are describing at the center of Able 2029 is not a neighborhood. It is a kingdom. And IC1101 is the king that has been sitting on that throne for nearly the entire lifetime of the universe, growing more massive with every passing epoch, as everything around it slowly, inevitably, falls toward its center. And this is where the emotional weight of the scale really lands for me. Because a spiral galaxy like ours still feels dynamic. It still feels like something in motion, something with structure, something with recognizable pieces. A supergiant elliptical like IC1101 feels different. It feels finished. It feels like something that has already lived through the exciting, star-forming, chaotic phase of its life and has now settled into a long, slow, ancient existence. Most of the stars inside it are billions of years old. Most of them are cool and reddish. There's very little new star formation happening. The gas that would fuel new stars has largely been used up, or expelled, or stripped away. What you are looking at is a graveyard of light. A vast, still, red-tinted mausoleum of stellar populations that were born in an era of the universe you and I will never see. When you look at that light, you are looking at the accumulated leftovers of billions of years of galactic activity that has now gone quiet. And that quiet is important because the size of IC1101 is not just a spatial fact, it is a historical fact. Everything about how big this galaxy is comes from what has happened to it over deep time. Nothing forms this large in one shot. Nothing gets born at this scale. Every enormous galaxy we know of, without exception, is enormous because of a very long, very violent history of eating other galaxies. And IC1101 sits at the exact gravitational bottom of one of the largest galaxy clusters within 1 billion light years of us, which means it has been at the receiving end of that history more thoroughly than almost anything else we have ever mapped. But I am getting ahead of myself, because before we can talk about how it grew, we need to make sure the scale itself is settled in your head. So let me put it one more way, using time. Consider what it would take to travel across IC1101 at the speed of light. Not slower, at the actual absolute universal speed limit. Nothing can go faster than this. Light traveling across the tightly bound body of IC1101 would take 600,000 years, not to reach it, just to cross it once. And if you took the outer halo figure, 4 million light years, then a beam of light crossing this single galaxy would take 4 million years to make the journey. 4 million years is roughly the amount of time that has passed since our earliest hominin ancestors were walking upright on the plains of Africa. If you launched a photon from one edge of IC1101's outer halo, when our earliest hominin ancestors were roaming the African plains, that photon would only now be arriving at the far edge. A single galaxy. One object. Long enough to hold the entire lineage of humanity from the earliest walkers to the current present as a single flash of light in transit. Now scale that against our galaxy. A beam of light crossing the Milky Way takes about 100,000 years to make the trip. That is already a stretch of time that predates every human city, every language, every recorded history. That is already staggering, and IC 1101 is somewhere between 6 and 40 times larger than that, depending on how you measure. There is no way to walk this idea back into normal human intuition. It just gets larger and larger the more you look at it. And when astronomers first started calculating these numbers with confidence, in the second half of the 20th century, some of them literally checked their arithmetic. They thought they had made a mistake. They thought no galaxy could be this big. And then they checked again, and the numbers held. Which brings us back to the promise of what I want to explore with you. Because a scale like this does not just appear. It has to be built. It has to be assembled, piece by piece, over billions of years of cosmic history. And the story of how a single object gets this large, sitting at the center of a specific kind of environment, doing a very specific kind of thing to its neighbors, is a story that touches on some of the deepest questions in astrophysics. It touches on how galaxies grow at all. It touches on why some galaxies stay small and some become monsters. It touches on what happens when gravity is given billions of years and a rich buffet of nearby galaxies to work with. And ultimately, it touches on a real puzzle. Because even our best current models of galaxy formation have some difficulty producing an object at this scale within the age of the universe. There's a genuine tension between what we see when we point our telescopes at IC 1101 and what our simulations predict should be possible. The object is real. The number is real. And yet, the theory strains to explain it. That tension is exactly what makes this galaxy so interesting to spend time with. But before we get to any of that, we need to understand what kind of galaxy this actually is. Because big is not a scientific classification. And IC 1101 is not just an enlarged version of the Milky Way. It is a fundamentally different kind of object in a fundamentally different environment, with a fundamentally different history. And once you understand what type of galaxy it belongs to, you will start to see why size, for this class of object, is not accidental. Size is the whole point. Size is the destiny of anything that ends up where IC 1101 has ended up. It could not have stayed small. Given enough time, given its location, this was always going to happen. What we are looking at is not really an anomaly. It is what happens when you take an ordinary galactic seed and put it at the exact center of one of the most gravitationally deep places in the observable universe, and then leave it alone for the entire history of everything. And what happens is monstrous by our standards. So let us take one more moment to sit with this. Our Milky Way, our entire galaxy, all of home, all of everything human beings have ever mapped in any real detail, would fit inside the halo of IC 1101 over 10,000 times if you compare volumes at the outer estimates. 10,000 Milky Ways, not stars, galaxies, whole galactic islands, all of them, dropped inside one gravitationally bound region, still with plenty of room. And the light from that region has been traveling toward us for over 1 billion years. And within that light, encoded in its brightness distribution, in its color gradients, in its faint outer envelope, is a record of a growth history so long and so violent that it defies casual explanation. When you point a telescope at IC 1101, you're pointing it at an ancient, quiet, ravenous thing. Something that has spent almost the entire lifespan of the universe pulling other galaxies down into itself. And we are only just beginning to piece together how it got that way. So we have this monster sitting 1 billion light years away. We have the raw scale. But if you asked an astronomer to describe IC 1101 properly, they would not lead with the size. They would lead with the type. Because size by itself does not tell you what a galaxy is. It tells you how much of one there is. And IC 1101 is not just a scaled up Milky Way. It is not a bigger spiral. It is not the same kind of object as the galaxy you live in, only larger. It is a completely different species of galaxy, belonging to a very specific and very rare class, and understanding what that class is turns out to be the key that unlocks everything else. Because once you know what type of galaxy this is, the size stops being an isolated mystery. The size starts to make a certain kind of sense, in the same way that a redwood tree makes sense once you know what a redwood is. You would not be surprised that a redwood is taller than a shrub. You would only be surprised if the shrub grew that tall. The question is not really, how did this thing get so big? The question is, what is it? And why does that kind of thing grow this big? So let me tell you what it is. There are broadly 3 families of galaxies that astronomers recognize. There are spirals like the Milky Way, with their beautiful flat disks and their winding arms and their busy ongoing star formation. There are irregulars, which are messier, often smaller, often disturbed by some recent interaction, with no clean symmetry to them. And there are ellipticals, which look from a distance like smooth, roughly egg-shaped clouds of stars. No arms, no disk, no dust lanes, just a soft, symmetric, glowing swarm of stars that fades gently from a bright center, out to a dim edge. Ellipticals range enormously in size. On the small end, you get dwarf ellipticals with only a few million stars. Tiny quiet objects that look almost like fuzzy globular clusters. On the large end, you get giant ellipticals containing hundreds of billions or trillions of stars that dominate whatever region of space they inhabit. And then at the very extreme end of that range, sitting apart from everything else in both size and location, you get a very specific subclass. A subclass so unusual, so distinct, so tied to a particular kind of environment that it gets its own name. That subclass is called CD elliptical, and IC 1101 is the poster child for it. The name CD is a bit awkward. It comes from a classification scheme developed by the astronomer William Morgan in 1958. The C stands for supergiant, borrowed from the way astronomers had long labeled the larger stars. And the D stands for diffuse, referring to that huge extended envelope of faint light. Put them together and you get supergiant diffuse, which is a fair description of what these galaxies are. But whatever the origin of the name, what it points to is a very real, very recognizable class of object. A CD elliptical is not just a big elliptical, it is an elliptical with a specific extra feature. It has a huge, extended, low surface brightness envelope of stars surrounding its main body. That envelope can stretch out for 1 million light years or more, glowing faintly, containing a substantial fraction of the galaxy's total mass in stars, but spread so thinly that in some places you can barely detect it above the background. It is that envelope that makes CD ellipticals look so extreme when you measure them generously. It is that envelope that pushes IC 1101 from giant elliptical territory into possibly the largest galaxy anyone has ever mapped territory. And it is that envelope that is at the heart of the honest scientific debate about how you measure objects like this. Let me linger on what this envelope actually is, because it is one of the more strange and beautiful features of the entire category. When you look at a normal elliptical galaxy, the brightness falls off in a fairly predictable way as you move outward from the center. Astronomers use a mathematical description developed by the French astronomer Gérard de Vaucouleurs in 1948 that captures how the light of a typical elliptical fades with distance from the core. It is a smooth, well-behaved curve, and most ellipticals follow it reasonably well out to their edges. But CD ellipticals do something different. Their inner regions follow the standard curve, but at some radius the light stops fading in the same way. Instead, it flattens out into an additional glowing halo that extends far beyond where a normal elliptical would end. That extra halo, that persistent glow that refuses to fade at the expected rate, is the defining feature. It is like a normal galaxy wrapped inside a much larger, dimmer galaxy. Or, more accurately, it is like a galaxy that has been generously coated in a thick layer of stars from somewhere else. Stars that did not originate in that galaxy at all, but that now belong to it through a process we will unpack shortly. That word, somewhere else, is important. And I want to flag it now, even though we are not going to unpack it fully yet. Because the diffuse envelope of a CD elliptical is not made of stars that formed in place. The stars in that envelope are, in large part, refugees. They came from other galaxies that used to exist as independent objects orbiting nearby, and that were dismantled, absorbed, and redistributed by gravity. The envelope is the tomb of those galaxies. That is why CD ellipticals only exist where they exist, which is the next crucial point I need to make. Because you do not find CD ellipticals floating alone in empty space. You do not find them at the edges of clusters. You do not find them scattered randomly through the universe. You find them in exactly one place. You find them at the gravitational center of the largest galaxy clusters. Every single one of them. This is not a coincidence. This is a defining property of the class, and IC1101 sits at the exact heart of the cluster it belongs to, a cluster called Able 2029, which is one of the most massive galaxy clusters within about 1 billion light years of us. Let me tell you what a galaxy cluster is, because this environment is going to matter enormously for everything else in this story. When astronomers first started cataloguing galaxies in the early 20th century, they noticed something interesting. Galaxies are not evenly distributed through space. They come in groups. Some galaxies live in small groups of a few to a few dozen. Our Milky Way lives in one of those, the local group, along with Andromeda and dozens of smaller companions. But some regions of space contain much larger collections. Hundreds or thousands of galaxies gathered into a single gravitationally bound structure, all orbiting a common center of mass, all held together by their mutual gravity plus the enormous amounts of hot gas and dark matter that fill the spaces between them. These are galaxy clusters. They are among the largest coherent structures in the universe. A single cluster can span 10 million light years or more, contain thousands of galaxies, and hold the mass of hundreds of trillions of suns worth of stars, gas, and dark matter combined, with the very largest clusters approaching a quadrillion solar masses. Able 2029 is one of these. It contains hundreds of galaxies, all swarming around a common center, and sitting at that center, at the exact gravitational bottom of the entire structure, is IC1101. Think about what it means for something to sit at the gravitational bottom of a system like that. Think about a deep bowl and imagine you keep dropping marbles into it. what happens? They roll down. They all end up at the bottom. That is what gravity does. Over long enough time, anything that can lose energy will drift toward the deepest point. And a galaxy cluster is one of the deepest gravitational potential wells anywhere in the universe. So over billions of years, objects inside the cluster tend to drift inward, especially the more massive ones, which lose orbital energy through a subtle gravitational drag effect called dynamical friction that we will get into later. The result is that the very center of a rich galaxy cluster is not just a place where a galaxy happens to sit. It is a place where any large galaxy that gets close enough will eventually end up. It is a place where galaxies collect. It is a place where they merge. It is a place where they pile up. And whatever galaxy gets to that center first and grows fastest tends to stay there and become the anchor around which everything else eventually falls. This is why CD ellipticals only form in cluster centers. It is not a coincidence, and it is not a design choice. It is a consequence of the physics of the location. Any galaxy that ends up at the exact gravitational bottom of a rich cluster is going to be repeatedly fed by other galaxies falling in from the surroundings. It cannot help but grow. It is like the drain at the bottom of a very slow, very cosmic sink. And the giant diffuse envelope that defines the CD class, that huge glowing halo of stars that extends for hundreds of thousands or millions of light years around the main body, is the accumulated debris from all of those infalling galaxies. When a smaller galaxy falls into a cluster and eventually reaches the center, it does not survive intact. It gets torn apart by tidal forces. Its stars get stripped off. Its outer regions get spread out into long streams. And those streams, over billions of years, get smeared into the diffuse envelope around the central galaxy. The envelope is not one galaxy's worth of stars. It is dozens of galaxies' worth of stars, mixed together, orbiting the central deep well, glowing faintly in the collective residue of everything that has been destroyed there. I want to sit with that image for a moment, because when you look at the outer halo of IC 1101, you are not looking at one galaxy. You are looking at the ruins of many. The faint glow that stretches out for 1 million or more light years around the main body is not the natural halo of a single galactic system. It is a graveyard. It is the accumulated stellar debris from every galaxy that has drifted too close to the cluster center over the past 10 or 11 billion years. Some of those galaxies were probably about the size of the Milky Way. Some smaller, some larger. All of them once were independent objects with their own histories, their own star formation, their own possibilities, and all of them, over immense stretches of time, were slowly pulled apart and folded into the halo of this one central object. When astronomers stare at that faint envelope through their deepest telescopes, they are staring at the mixed remains of a very long history of dismantling. That is what a CD elliptical is at its core. It is a monument built out of victims. Now, this is also where I need to come back to the honest caveats about the size of IC 1101, because now the phrase largest galaxy starts to have a meaning we can actually pin down. The question of size becomes a question of where you decide the graveyard ends. If you draw a line at the bright, dense, tightly bound stellar body, the number you get is somewhere around 600,000 light years across. That is the region where the stars are clearly part of the main galaxy, densely packed, moving in coherent gravitational patterns. If you draw a line at the outer edge of the extended diffuse envelope, out where the light finally fades below what you can distinguish from the intergalactic background, the number you get can climb toward 2, 3, or even 4 million light years. Different astronomers, using different surveys and different sensitivity thresholds, have published different numbers. Some earlier studies from the 20th century put the outer halo at figures that are now considered generous. More recent, deeper imaging suggests the halo is genuinely huge, but the exact edge is a matter of definition rather than measurement. And here is a related point that is worth being careful about. When you compare IC 1101 to other candidates for the largest galaxy, you have to be sure you are measuring them the same way, because there are other supergiant ellipticals at the centers of other rich clusters, and some of them, measured with generous halo definitions, come out in the same range. The famous M87 at the center of the Virgo cluster is a genuinely enormous CD elliptical, though it is smaller than IC 1101 by most measures. There are others, further away, in more massive clusters that may be comparably huge. There are also so-called protocluster central galaxies at very high redshifts that may end up rivaling any of these once they finish their growth. So the honest scientific position, and the one I want you to walk away with, is not that IC 1101 is unambiguously the biggest galaxy in the universe. The honest position is that it is one of a small handful of contenders in a category of extreme central cluster ellipticals, all of which are so vast that arguing about which is largest depends entirely on how you draw the edges. But this does not make IC 1101 any less astounding. In some ways, it makes it more interesting, because what we are really describing is not a single freakish outlier. What we are describing is a category of objects, a class of galactic monsters that only exist in one very specific place in the universe and that only get made through one very specific process. And IC 1101 is one of the most spectacular examples of that class. It is at the top end of a bell curve that already sits far to the right of anything you can find in any other environment. It is one of the biggest of the biggest. That is a scientifically defensible statement. That is worth all the awe. It is worth spending a moment on what the other supergiant central galaxies actually look like, because they help you see that IC 1101 is not alone in this category, and that the puzzle is a class-wide one rather than a single object oddity. At the center of the Phoenix cluster, one of the most massive galaxy clusters ever discovered, sits a central galaxy that is itself an extreme CD elliptical. It is unusual because unlike most CD ellipticals, it is currently forming new stars at a very high rate, suggesting that the black hole feedback in that particular system is not keeping up with the amount of gas trying to cool onto it. Its central galaxy is not as large as IC 1101 by most measures, but it is illustrative of the extremes that this category can produce, and of how sensitive the final outcome is to the balance between feeding and feedback. At the center of the Coma cluster, one of the best studied nearby galaxy clusters, sit two dominant giant ellipticals side by side, a slightly different configuration from IC 1101, but produced by similar processes. There are also more distant candidates, discovered by deeper surveys of more massive clusters, that may eventually rival or exceed IC 1101 when measured with the same generous halo definitions. Some of them are in clusters so massive and so distant that our current instruments cannot yet map their outer envelopes with the precision we would need to make a fair comparison. The point is that IEC 1101 is not a lone freak. It is one of a small population of extreme central galaxies scattered across the observable universe, all of which push against the same theoretical limits. When astronomers argue about which one is truly the largest, they are really arguing about how you draw the edges of a category of objects that all sit near the top of the same distribution. That argument is technical and interesting, but somewhat beside the point of the deeper mystery, which is why the distribution has a top end where it does it all, and why several objects have managed to reach that top end. Whatever explanation eventually resolves the theoretical tension for IC 1101 will also have to resolve it for the others. The puzzle is not, this one specific galaxy is too big. The puzzle is, the class of most extreme central galaxies is bigger than our models comfortably predict. That reframing matters because it turns the discussion from a single anomaly into a systematic feature of the universe that our theories will need to accommodate as they get refined over the coming decades. Let me also spend a little time on what the mass of this thing is, because that gives you another window into what makes it strange. Astronomers typically talk about galaxy mass in units of solar masses, meaning the mass of our sun. The Milky Way is estimated to have a total stellar mass of somewhere in the range of 50 to 60 billion solar masses. IC 1101, in its main body, comes in at somewhere around 1 to 3 trillion solar masses of stars, depending on the study, with even higher estimates when the diffuse envelope is included. That is roughly 20 to 50 times more stellar mass than our galaxy in the central body alone, and more when the outer halo is added in. And if you include the dark matter that surrounds and permeates the whole thing, which is the invisible material that only interacts through gravity but which dominates the mass budget of every galaxy and cluster, the total mass associated with the galaxy and its immediate surroundings rises substantially higher, and the wider cluster it anchors has a total mass on the order of 100 trillion solar masses, when you include all its galaxies, hot gas, and dark matter combined. This is not just a large galaxy. This is a large galaxy embedded in one of the deepest gravitational structures in the observable universe, and the two are inseparable. You cannot have IC 1101 without Able 2029. You cannot have the galaxy without the cluster. The galaxy is what the cluster produced. At the very heart of this galaxy sits something even more extreme, though on a very different scale. Like most large galaxies, IAC 1101 hosts a supermassive black hole at its core. But the black hole at its core is not just supermassive in the ordinary sense. Measurements based on scaling relations suggest that the central black hole of IC 1101 has a mass in the range of tens of billions of solar masses, with some estimates pushing as high as 40 billion or more, depending on the model and the assumptions. That is thousands of times more massive than the black hole at the center of the Milky Way, which weighs in at around 4 million solar masses. It is one of the largest black holes ever measured. And this is not accidental either. There is a well-established correlation discovered in the late 1990s between the mass of a galaxy's central bulge and the mass of the supermassive black hole living at its center. Bigger galaxies host bigger black holes. And when you have the largest kind of galaxy sitting at the center of a rich cluster, having grown by devouring other galaxies over billions of years, you also get a proportionally monstrous black hole sitting at its heart. The two grew together. Every galaxy that fell into IC 1101 and got absorbed also probably contributed to the growth of the central black hole, and the result is a gravitational monster nested inside a galactic monster, nested inside a cluster monster. Let me pull all of this together into a single clean picture. What we are looking at when we look at IC 1101 is this: a supergiant CD elliptical galaxy sitting at the exact gravitational center of a massive galaxy cluster called Abell 2029, roughly 1 billion light years from Earth. The main body of the galaxy is somewhere around 600,000 light years across and contains something like 100 trillion stars, most of them old and red. That main body is surrounded by an enormous, diffuse envelope of stars that stretches out for hundreds of thousands or even a few million light years, glowing faintly, containing the accumulated debris of many other galaxies that have been dismantled at the cluster center over cosmic history. At the very core of the galaxy sits a supermassive black hole that itself is one of the largest ever measured, weighing in at tens of billions of solar masses. And this entire structure is embedded in a dark matter halo that dwarfs the visible mass of the galaxy, providing the invisible gravitational scaffolding that binds everything together. Every part of this description is intertwined with every other part. The cluster produces the central galaxy. The central galaxy produces the diffuse envelope. The mergers produce the black hole. The dark matter holds it all together. You cannot pull one piece out without losing the sense of the whole. It is one integrated cosmic structure, forged over billions of years of gravity doing what gravity does. And the reason understanding what kind of galaxy this is matters so much is that once you see it as a CD elliptical at a cluster center, the enormous size stops being a mystery in isolation. It becomes an expected consequence of the environment. Anything that ends up in the situation IC 1101 is in was always going to become gargantuan. The only question is exactly how big, and exactly how quickly. And here is where the real puzzle starts. Because even though we understand the general reason CD ellipticals are large, our detailed models of galaxy formation still have trouble producing objects at exactly this scale within the age of the universe. That tension is something we will come back to. But for now, what I want you to hold in mind is this. IC 1101 is not just a bigger version of a normal galaxy. It is a specific type of object, born in a specific type of environment, sitting at the bottom of one of the deepest gravitational wells in the known universe, surrounded by the ghostly remains of everything that has fallen in with it. The size is the type is the size. And now that we understand what it is, we can finally start to understand how it got that way. So we have this monstrous galaxy sitting at the bottom of its cluster, and we know what type of object it is, and we know that objects of this type only exist in one very specific kind of environment. But we still have not answered the actual question. How does something get this big? How does any single galaxy accumulate 100 trillion stars and stretch across hundreds of thousands or millions of light years? The stars did not appear inside IE's 1101 all at once. There was never a moment where a giant cloud of gas collapsed and instantly formed a galaxy this enormous. That is not how galaxies form. That is not how anything in the universe forms at this scale. Everything big is made of pieces. Everything big had to be assembled, and the process by which IC 1101 was assembled is one of the slowest, most violent, and most patient acts of construction anywhere in nature. It is called hierarchical merging. And once you understand it, the size of this galaxy stops feeling like an anomaly and starts feeling like a very long, very careful crime scene. Because this galaxy did not just grow, it ate. And it kept eating. And it is still eating right now. And it has been eating for nearly the entire history of the universe. Let me build this up carefully, because the physics of galactic cannibalism is genuinely beautiful and genuinely strange, and I want you to see how the pieces fit together. Start with the earliest era. Roughly 13 billion years ago, not long after the Big Bang, the universe was much smaller, much denser, and much more chaotic than it is today. Matter was clumping together under gravity into small collapsed structures. These early clumps were mostly dark matter, that invisible substance that only interacts through gravity, providing the scaffolding on which everything else would eventually be built. Ordinary matter, made of the atoms you and I are made of, fell into those dark matter clumps and began to cool and collapse further, forming the first stars and the first tiny proto-galaxies. These first galaxies were small. Some of them were only a few million or a few 100 million stars each. They were nothing like the majestic spirals or supergiant ellipticals we see today. They were seeds. They were embryonic. They were the raw material from which everything else would be built. And here is the key insight. From the moment those first galaxies formed, they started merging. Some of the small proto-galaxies happened to form close to each other, embedded in the same larger dark matter clumps. Gravity pulled them together. When two of them collided, they did not shatter or bounce off. They combined. Their stars mixed. Their gas pooled. Their dark matter halos merged into one larger halo. And the result was a slightly bigger galaxy, sitting inside a slightly deeper gravitational well, ready to pull in the next round of neighbors. This process happened again and again. Small galaxies merged into medium galaxies. Medium galaxies merged into larger galaxies. And in the regions of the universe where the initial density of dark matter was highest, the mergers happened fastest and most often. Because in those dense regions there were more nearby galaxies, more gravitational pulling, more collisions per unit of time, and over billions of years, the mergers in the densest regions built up ever larger and larger galaxies, feeding on the neighbors until eventually one dominant object emerged at the center of every rich collapsed region. This is hierarchical merging in its simplest description. Small things merge to make medium things. Medium things merge to make big things. Big things merge to make giants. And the monsters end up at the centers of the deepest gravitational wells, because that is exactly where the mergers concentrate. Because the word collision is misleading. When you hear it, you probably picture two cars smashing into each other, or two billiard balls clacking off. Something violent, sudden, and messy. But a galactic collision is nothing like that. Galaxies are almost entirely empty space. The stars inside a galaxy are separated by enormous distances relative to their own sizes. Our sun is about 1.4 million kilometers across, and the nearest star to us is about 40 trillion kilometers away. That is a ratio of roughly 1 to 30 million. If you scale the sun down to the size of a grain of sand, the nearest star would be tens of thousands of kilometers away, farther than the distance across an entire continent. The space between stars is empty on a scale that human intuition cannot really cope with. So when two galaxies collide, almost none of their stars actually hit each other. They pass through each other's territory like two swarms of bees passing through the same field. The stars slide past one another at enormous distances, and the individual stars, taken one at a time, are barely disturbed. But that does not mean the galaxies are unaffected. Far from it. While the stars rarely collide, their gravitational fields interact intensely. When two galaxies pass through each other, every star in each galaxy feels the collective gravitational pull of every star in the other galaxy. And that pull distorts their orbits. Stars that were previously moving in nice organized patterns get flung into chaotic new trajectories. Long streams of stars get pulled out of both galaxies into arcing tidal tails that can stretch for hundreds of thousands of light years. Gas clouds, unlike stars, do actually collide, because gas fills space more evenly and cannot slip past itself the way stars can. So the gas gets compressed, shocked, heated, and triggered into intense bursts of new star formation. And the two galaxies, after passing through each other once, do not simply continue on their separate ways. They have lost energy to gravitational interactions, and that loss of energy means they cannot escape each other anymore. So they swing back, pass through each other a second time, then a third, each pass mixing their contents more thoroughly. And eventually, after several passes, they settle into a single, merged, roughly egg-shaped, elliptical galaxy. The spirals get destroyed, the disks get puffed up into a smooth, spheroidal shape. The gas gets used up in the merger-triggered starburst, and what remains is a bigger elliptical galaxy, quieter and older than either of the two galaxies that made it. I want to slow down here and talk about what happens to the gas during a merger, because it turns out to matter enormously for what the final galaxy looks like. When astronomers study mergers, they draw a distinction between what they call wet mergers and dry mergers. A wet merger is one between two galaxies that both still contain substantial reservoirs of cold gas. That gas is the raw material for making new stars. When two gas-rich galaxies collide, their gas clouds do actually run into each other, which is different from what happens to their stars. The gas gets compressed by the shock of the collision, and compressed gas cools, and cool gas collapses under gravity, and collapsing gas forms new stars. A wet merger triggers an intense burst of star formation that can last for tens of millions of years, briefly making the merged galaxy one of the brightest and most active objects in its part of the universe. But then, after the burst, most of the gas is gone. It has been used up in the starburst, or blown out of the galaxy by the intense stellar winds from all the new massive stars, or driven into the center where the newly awakened supermassive black hole can feed on it, and blast the remainder out with jets and radiation. Either way, the wet merger consumes its own fuel. And once the gas is gone, the merged galaxy cannot form significant numbers of new stars anymore. It becomes red and quiescent, dominated by the older stars that survived from the two original galaxies. A dry merger is different. A dry merger happens between two galaxies that have already used up most of their gas. There is no big starburst, because there is not much gas left to compress. There is no dramatic new generation of blue stars, because there is not much material to make them from. What happens instead is that the stars from the two galaxies simply mix together, gravitationally, without adding new light or new stellar populations. The merged galaxy ends up as a bigger, quieter, redder version of what went in. And here is the crucial point for our story. The mergers that built IC 1101 over the last several billion years have been overwhelmingly dry mergers. The early mergers, back near the beginning of cosmic history were probably wet, and they contributed most of the actual star formation that put stars into the galaxy in the first place. But by the time the universe was a few billion years old, most of the galaxies falling into the cluster center had already burned through their gas or had it stripped away, and the mergers became dry. This is why the interior of IC 1101 is so uniformly old and red. It has been assembling for billions of years without meaningful new star formation. Every galaxy it eats now contributes stars that were already old when they arrived. There is also a beautiful piece of physics that happens during the merger itself, called violent relaxation, and it is worth understanding because it explains how you go from two organized spiral disks to a single smooth spheroid. When two galaxies collide, the gravitational field they generate together is not static. It is rapidly changing as the galaxies pass through each other, as their centers of mass shift, as their internal structures distort. Stars orbiting in that rapidly changing field do not follow simple orbits anymore. They get thrown into chaotic trajectories, and over the course of a few 100 million years, their orbits get thoroughly randomized. The nice organized rotation of a spiral disk gets erased. The stars end up on orbits that are oriented in all different directions. Some plunging through the center on radial paths, some looping around in tilted ellipses, some almost circular. The collective result is a smooth, spheroidal distribution with no preferred axis and no coherent rotation. That is what an elliptical galaxy is at its heart, and violent relaxation is the mechanism that turns disk mergers into ellipticals. Every time IC 1101 has absorbed a smaller galaxy, the incoming stars have been fed through this violent relaxation process, and they have ended up joining the smooth, chaotic, non-rotating stellar sea that makes up the main body. That is why the whole galaxy is one uniform shape, rather than a mess of preserved substructures. The mergers have been literally shuffling the stars into random orbits for billions of years. This is why elliptical galaxies exist at all. Every large elliptical you can point a telescope at is very likely the product of one or more major mergers between disk galaxies. And every CD elliptical, like IC 1101, is the product of many mergers, stretching over billions of years, in an environment where mergers happen especially often. The reason I want you to see this so clearly is that once you understand what a merger physically does, you understand why cluster centers become graveyards of galactic material. Every merger destroys structure. Every merger takes two galaxies and turns them into one blob. Every merger flings some stars out into a diffuse outer envelope. And when you do this over and over and over again for 11 or 12 billion years, in a place where infalling galaxies keep arriving from all directions, you get exactly what we see when we look at IC 1101, a vast, smooth, quiet red central body surrounded by a massive halo of stellar debris. It is not one galaxy. It is the fused, digested corpse of an enormous number of galaxies, all merged into a single object with a single center of gravity. But there is another crucial piece of the story, and this is the piece that makes cluster centers so special. Not just any location in the universe experiences constant mergers. Most galaxies out there are actually pretty isolated. The Milky Way, for example, is in a fairly modest environment. We do have neighbors. Andromeda is on a collision course with us and will merge with us in a few billion years. We have some smaller satellite galaxies that we are slowly pulling apart, but we are not in the kind of dense environment where a new galaxy falls into us every few 100 million years. we are in a relatively quiet neighborhood. Galaxies in low-density environments merge slowly or infrequently, or not at all after their early growth phase. The mergers that happen tend to be with small satellites, which do not add much mass. So galaxies in low-density environments tend to end up moderately sized, disc-shaped, with orderly ongoing star formation. Galaxies like the Milky Way. But the story is entirely different in the center of a rich galaxy cluster. In a cluster center, mergers do not stop. They keep going, epoch after epoch, because the environment keeps feeding new galaxies into the system. Here is the physics of that feeding, and this is where things get really elegant. A galaxy cluster is not a static collection of galaxies at fixed positions. It is a dynamic system in which the galaxies are all orbiting a common center of mass. Their orbits carry them in loops around the cluster, closer to and farther from the center over time. And crucially, those orbits are not perfectly stable. There is a subtle gravitational drag effect that slowly saps orbital energy from the larger galaxies, causing them to spiral inward over billions of years. The dynamics of this effect were worked out mathematically in the 1940s by the astrophysicist Chandrasekhar, and it is one of the most important processes in all of galactic dynamics. Let me explain how it works, because it is one of the most beautiful pieces of gravitational physics you can encounter. Imagine a large galaxy moving through a region of space that contains many smaller galaxies and lots of dark matter. As the large galaxy moves, its gravity attracts everything around it, so it pulls the smaller nearby matter toward itself. But the large galaxy is moving, so by the time the nearby matter reaches where the large galaxy was, the large galaxy has moved on. What happens is that the pulled matter piles up slightly behind the moving galaxy, forming a subtle overdense wake in its trail. That wake, with its extra concentration of mass, then exerts a gravitational pull back on the large galaxy. Since the wake is behind the galaxy, the pull is backward. And a backward pull on a moving object is a drag force. It slows the galaxy down. Not by much per orbit, but over billions of orbits, it adds up. The galaxy loses energy. Its orbit shrinks. It spirals inward toward the cluster center. And eventually, after enough billions of years, it arrives at the very bottom of the cluster's gravitational well, which is exactly where C1101 is waiting. But dynamical friction is not the only thing that happens to a galaxy falling into a cluster. There is another process going on at the same time. It also contributes to the growth of the central galaxy in an indirect way. The space between galaxies in a rich cluster is not empty. It is filled with an enormous amount of hot gas, called the intracluster medium, at temperatures of tens or hundreds of millions of degrees. This gas has been heated by the gravitational collapse of the cluster itself, and by all the merger activity that has happened over the cluster's history. And when a galaxy falls into the cluster and starts moving through this hot gas at hundreds or thousands of kilometers per second, something dramatic happens. The gas outside the galaxy pushes against the gas inside the galaxy, exerting a pressure. That pressure is called ram pressure, and if the galaxy is moving fast enough through dense enough intracluster medium, the ram pressure can strip the galaxy's own gas right out of it. The gas gets torn away from the galaxy's gravitational hold and left behind as a long trailing wake, joining the intracluster medium. And once a galaxy has lost its gas, it can no longer form new stars. It becomes quiescent. It becomes red. It becomes exactly the kind of gas-poor galaxy that will produce dry mergers when it eventually spirals into the cluster center. So ram pressure stripping and dynamical friction work together in a kind of two-stage process that shapes what feeds IC 1101. First, the infalling galaxy loses its gas to ram pressure as it moves through the intracluster medium during its orbits around the cluster. Then, over a much longer time scale, it loses its orbital energy to dynamical friction and spirals inward. By the time it arrives at the center and gets absorbed, it is already a gas-poor, red, quiescent galaxy, which is exactly why the mergers that build up the outer body of IC 1101 are dry ones that do not produce new stars. The environment has been preparing each meal for billions of years before it finally gets served. I also want to mention what happens to the dark matter during all of this, because dark matter is the invisible scaffolding on which everything else is built, and its behavior in mergers is important. When two galaxies merge, their dark matter halos do not simply add together into a bigger halo of the same shape. The dark matter also undergoes its own version of violent relaxation, mixing and settling into a new configuration. And crucially, the dark matter halo of the merged galaxy is much more extended than the halo of either original galaxy alone. It reaches out further from the center, and that extended halo provides the gravitational binding that keeps the diffuse stellar envelope in place. Without a truly enormous dark matter halo around IC 1101, the stars in the outer envelope would not be gravitationally bound. They would fly away. So every merger that adds stars to the outer regions of IC 1101 also has to add dark matter around them to keep them bound. Both components grow together, invisibly linked. When we say IC 1101 has a total mass of many trillions of suns, we are including both the visible stellar mass and the invisible dark matter that surrounds and supports it, and both are the accumulated products of billions of years of mergers. The dark matter halo of this galaxy is one of the most massive gravitationally bound structures anywhere in the observable universe, and it is what makes the entire diffuse envelope physically possible. This is the pump that feeds a CD elliptical. Dynamical friction is the mechanism that continuously delivers galaxies from the outer regions of the cluster to the central engine. Every galaxy in Able 2029 that is large enough for dynamical friction to significantly affect it is, over time, slowly spiraling toward IC 1101. Some of them arrive quickly on cosmic timescales if they were massive enough or unlucky enough to start close to the center. Others take much longer, orbiting for billions of years before finally succumbing. But the direction of flow is one way: in toward the center, toward the monster. And when they finally arrive, when their orbits have decayed enough that they can no longer stay in the outer cluster, and they fall into the deep, central gravitational well, they meet the same fate every time. They get absorbed, they get torn apart, their stars get folded into the central body of IC 1101. Their outer regions get spread into the diffuse envelope. Their central black holes, if they had them, spiral down through the same dynamical friction process and eventually merge with the central supermassive black hole. And IC 1101 grows a little bit more. Let me put a number on this to make it concrete. Simulations of cluster evolution suggest that the central galaxy of a rich cluster like Able 2029 has probably absorbed somewhere on the order of dozens of galaxies of significant size over its lifetime. along with many more minor accretion events. Some of those were small dwarf galaxies, contributing modest amounts of stars. Others were substantial galaxies, comparable in mass to the Milky Way, contributing hundreds of billions of stars each. Not all of them arrived at the same time. The mergers happened in waves, distributed across the entire history of the cluster. Some happened very early, when the universe itself was young and the first proto-galaxies were still forming, and the merger rate was fantastically high. Some happened later, as the cluster continued to grow by pulling in galaxies from the surrounding cosmic web. Some may have happened in the last few billion years, at a slower but still non-zero rate, and a few are probably happening right now, in the sense that there are galaxies within Abell 2029 whose orbits are decaying toward Wyattsey 1101 at this very moment, and that will, over the next few billion years, be pulled into the central body and absorbed. The process has not stopped. It has only slowed. I want to give you a sense of what one of these absorption events actually looks like when you play it back in cosmic time. Imagine a fairly ordinary spiral galaxy, roughly Milky Way sized, orbiting somewhere in the outskirts of Abell 2029 about 10 billion years ago. It has its own stars, its own gas, its own dust lanes, its own supermassive black hole at the center. It is a normal galaxy, doing what a normal galaxy does, but its orbit is not stable in the long term. Dynamical friction is slowly but steadily robbing it of energy. Over the next several billion years, its orbit tightens. It spirals inward. Each pass through the cluster brings it closer to the center. Eventually, on one of those passes, it gets close enough to IC 1101 that the tidal forces from the central galaxy start to distort its shape. Long streams of stars get pulled out of its outer regions into arcing tails. Its gas gets compressed and triggered into a final burst of intense star formation. Its once orderly spiral structure begins to dissolve, and then on the next pass, or the one after that, it comes close enough that it cannot escape anymore. It falls into the central galaxy. Its remaining structure comes apart. Its inner stars settle into the central body of IC 1101, contributing to the dense core. Its outer stars get flung into the diffuse envelope, contributing to the vast surrounding halo. Its supermassive black hole, itself dragged inward by dynamical friction, acting on its own smaller scale within the merging galaxy, eventually spirals down to the center and merges with the central supermassive black hole of IC 1101, releasing an enormous burst of gravitational waves and adding its mass to the already colossal central object. And what remains is a slightly larger central galaxy, a slightly deeper gravitational well, and one fewer independent galaxy in the cluster. Now repeat that. Not once, not 10 times, repeat it dozens or hundreds of times, spread across most of cosmic history, each merger contributing a little more to the central object, each merger deepening the well, each merger increasing the rate at which the next merger will happen. This is why CD ellipticals become so large, not because of any single dramatic event, but because of a slow, patient, relentless accumulation. It is not one meal. It is a very long feast, spread across nearly the entire lifetime of the universe. And the diner does not stop. As long as there are galaxies in the cluster that can be pulled inward by dynamical friction, the central galaxy will keep growing. The rate has slowed compared to the early universe because the universe as a whole has become less dense as it has expanded, and because many of the easiest mergers have already happened, but it has not stopped. IC 1101 is still growing today. Not fast, not dramatically, but steadily. And here is a piece of the picture I want to make sure lands, because it changes how you think about the diffuse envelope. Every time a galaxy is absorbed, most of its inner stars end up in the central body, but the outer stars get flung outward by tidal forces. Some of those stars get flung so far that they end up on very long, very slow orbits around the central galaxy. Orbits that carry them out to hundreds of thousands or even millions of light years before curving back. Those distant orbiting stars are what make up the extended envelope. They are not stars that formed in place, they are the outer layers of galaxies that were digested at the center. They are still gravitationally bound to IC 1101, but only loosely. They spend most of their time far from the main body, drifting through nearly empty intergalactic space, glowing faintly. And because so many galaxies have contributed to that envelope over so many billions of years, the total number of stars out there is enormous, even though their density is very low. This is why depths in astronomical imaging matter so much. When early astronomers looked at IC 1101 with modest instruments, they saw the bright central body and a small halo, and that is what they measured. As telescopes got bigger and detectors got more sensitive, they could image fainter and fainter structures around the galaxy. They kept finding stars, kept finding more envelope, kept pushing the measured size outward, and every time they went deeper, they saw more of the accumulated debris. This is the source of the disagreement I keep flagging about how big IC 1101 really is. The answer depends on how deep you look. The stars are out there. The envelope is real. The question is only where you decide to stop counting them. And that is not a fault of the measurement. It is a fundamental property of what this kind of galaxy is. A CD elliptical does not have a clean edge, because the process that made it did not leave clean edges. It smeared galaxies out over enormous volumes, and the smearing is what we see. Let me also address one more piece of the puzzle, which is why so few galaxies grow to this scale. Because if hierarchical merging is a universal process, and if the universe is full of galaxies, why is not every galaxy the size of IC 1101? Why do most galaxies stay small, or medium, or merely large, instead of becoming absolute monsters? The answer is environment, and this is worth being clear about. Hierarchical merging depends on having neighbors close enough to merge with. It depends on being in a gravitational potential well deep enough to gather more material over time. And it depends on being in a region of space where the initial density of dark matter was high enough that a rich structure could form. Most galaxies are not in that situation. Most galaxies are in modest environments, with a few small companions in shallow gravitational wells. They merge with their small companions early in their history, and then coast, growing very slowly or not at all, once the local supply of mergers runs out. Only a tiny fraction of all the galaxies in the universe are in the specific situation of being the largest galaxy at the center of a very rich cluster. And only those galaxies become CD ellipticals. The Milky Way, in its quiet suburban environment, will never become IC 1101. Even when it merges with Andromeda in a few billion years, the resulting elliptical will still be modest by CD standards. Because we are not sitting at the bottom of a cluster. We are not on the receiving end of decayed orbits from hundreds of galaxies. We are just a normal galaxy in a normal neighborhood. Which brings me back to the central point about IC 1101 and why it is the size it is. The galaxy sits at the exact gravitational bottom of one of the most massive galaxy clusters, within 1 billion light years of us. Everything about its size, its type, its diffuse envelope, its monstrous central black hole comes from that single geographic fact. Its location is its destiny. Its address is its history. It grew this large because of where it is. It became a CD elliptical because of where it is. It has absorbed dozens or hundreds of galaxies because of where it is. And it will keep growing, at a slower rate but still non-zero, for as long as the cluster continues to exist, and as long as there are galaxies within it that can spiral inward under dynamical friction. This is the mechanism. This is the whole story of how something gets this big. Not a single event, not a single collapse, but a very long, very patient act of consumption spread across nearly the entire history of the universe, in a very specific location where the physics of gravity has been given every possible advantage. When you look at IC 1101, you're looking at what gravity does when you let it work uninterrupted at the center of a rich cluster for 11 or 12 billion years. And what gravity does, given those conditions, is build a monster, slowly, steadily, and with a patience that dwarfs every timescale we know how to measure. So now we have the mechanism. We understand what IC 1101 is, and we understand how it got that way. And you might think that would be the end of the story. A supergiant galaxy sits at the center of a rich cluster. Dynamical friction feeds at galaxies over billions of years. Mergers pile up, the diffuse envelope grows, and eventually you get a monster. Clean explanation. Case closed. Move on. Except that when astronomers actually try to run the numbers, when they build detailed computer models of how galaxy clusters evolve from the early universe to the present day, when they simulate the merger histories of central galaxies in rich clusters and see how big they end up, they run into a real problem. The models struggle to build IC 1101 within the age of the universe, not by a small margin, in some cases, by a lot. The mechanism we just described, which is the leading and best supported explanation for how CD ellipticals grow, does work. It does produce enormous central galaxies. But when researchers push the simulations to their limits, when they try to reproduce the most extreme objects at the top end of the observed size and mass distribution, the theory strains. And the object that puts the most pressure on the theory, the one that sits at the extreme tip of the observed distribution and refuses to make life easy for the modelers, is IC 1101 and the small handful of other supergiant central galaxies like it. So, the honest, scientific position, and the one I want you to hold in mind as we work through the last stretch of what we are exploring, is this. We know how galaxies like this grow. What we do not fully know is why some of them end up as extreme as they do. Let me spell out where the tension actually lives, because I want you to see it clearly rather than just being told there is a puzzle. The universe is 13.8 billion years old. That is a lot of time, but it is also finite. Every merger that has ever contributed to the growth of IC 1101 had to happen within that window. Every galaxy that spiraled into the cluster center under dynamical friction had to complete its slow decay within that window. Every star that now sits in the diffuse envelope had to originally form in some smaller progenitor galaxy, and then that progenitor had to fall inward, and then it had to be disrupted, and then its stars had to settle into their current distant orbits, all within that same window. And crucially, the mergers that matter most for building up the central body of a CD elliptical are what astronomers call major mergers, meaning mergers between two galaxies of roughly comparable size. Minor mergers, where a big galaxy absorbs a small one, add mass slowly. Major mergers add mass fast, but major mergers are rare. Even in the dense environment of a cluster center, they do not happen every 100 million years. And when you count them up in simulations, and you calculate how much total mass could plausibly be assembled into a single central galaxy over the age of the universe, the numbers come out uncomfortably close to what we actually see in the most extreme cases. Sometimes uncomfortably below. The models can, with the right ingredients, reproduce galaxies as big as most of the observed CD ellipticals. But at the very top end of the distribution, where IC 1101 sits, the fit is tight and some model runs simply do not get there in time. This is what physicists call a tension, and it is a very specific kind of tension. It is not a contradiction. Nobody is claiming that IC 1101 violates the laws of physics. Nobody is claiming that our understanding of galaxy formation is fundamentally broken. The mechanism is right. The physics is right. The general story of hierarchical merging is one of the best supported ideas in modern cosmology, with mountains of observational and simulation evidence behind it. But at the extreme edge of what the theory predicts, we find objects that push the theory as far as it can go, and IC 1101 is one of those objects. It is a test case. It is a stress test on the model. And when a real object stress tests a model, there are only a few possibilities for what is going on. The first possibility is that the model is basically right, and we just need to be more careful about the ingredients, the initial conditions, and the timing. The second possibility is that we are misunderstanding something about the object itself, that our measurements of IC 1101 size or mass are being biased in some way that makes it look more extreme than it really is. The third possibility is that there is a piece of the physics we are missing, something that lets galaxies at the top end of the distribution grow faster or more efficiently than our current models allow. Each of these possibilities is being explored right now by real researchers, and none of them has been ruled out. So let me walk through each one, because they represent the leading edge of how astronomers think about objects like this today. Start with the first possibility. Maybe the model is right, and we are just close to the edge. This is actually the most common view in the field, and it has real merit. Detailed simulations of galaxy cluster evolution have improved enormously over the past couple of decades. Modern simulations include not just gravity, but also the physics of gas cooling, star formation, supernova feedback, black hole accretion, and jets from active galactic nuclei. They can track billions of individual mass elements across billions of years of simulated time. And when researchers run their most sophisticated simulations, tuned to match the observed properties of galaxy clusters in general, they do produce central galaxies that come reasonably close in size and mass to the most extreme observed CD ellipticals. Not always, not in every simulation run, but in a non-trivial fraction, which suggests that objects like IC 1101 may just be at the rare upper tail of what the standard model predicts, achievable if the initial conditions are especially favorable and the merger history is especially productive. This is a comfortable position for the field. It says the model is fine, but only just. and IC 1101 happens to sit at the edge of that fine. This is probably true for most CD ellipticals. Whether it is true for the very biggest of them, at the very top of the distribution, is where the honest debate continues. The second possibility is that we are misreading the object itself, and this is more subtle than it might sound. Because remember the question of where you draw the edge of IC 1101 and what you count as part of the galaxy. When someone says this galaxy has a mass of 100 trillion solar masses and stretches for 1,000,000 light years, those numbers come with error bars, and the error bars can be surprisingly wide. The stellar mass in the diffuse envelope is very hard to measure precisely, because the light is so faint and so spread out that separating it from the intergalactic background and from foreground contamination is a serious technical challenge. Different studies, using different techniques, sometimes disagree by factors of 2 or 3 about the total stellar content of the envelope. And if the envelope is smaller or less massive than the highest estimates suggest, then the model does not need to work as hard to build it. The tension eases. The puzzle softens. There is also an interesting subtlety about what counts as part of IC 1101 at all. Because in a rich galaxy cluster, there is a component called the intracluster light. This is a diffuse background glow that fills the space between the galaxies in the cluster, made up of stars that have been stripped from their original host galaxies by tidal forces, and now drift through the cluster on unbound or loosely bound orbits. The intracluster light is real, and it is significant. And in the outer regions of a cluster, it can be a substantial fraction of all the light. And here is the tricky part. Where does the diffuse envelope of the central CD galaxy end? And where does the intracluster light begin? Some astronomers argue that the distinction is meaningful and that they are physically different components. Others argue that the diffuse envelope of a CD elliptical and the intracluster light of its host cluster are essentially the same thing viewed from different angles, and that trying to separate them is somewhat artificial. If you take the second view, then a substantial fraction of what gets counted toward IC 1101's mass in the most generous measurements might really be cluster-wide diffuse light that does not belong to any single galaxy at all, which would mean that the true central galaxy is smaller than the extreme numbers suggest, and the theory does not need to explain quite so much. Again, this softens the puzzle without eliminating it. The third possibility is the most interesting one, and it is where the real theoretical frontier lies. Maybe our current models of galaxy formation are missing a piece of physics that would let extreme central galaxies grow faster than we currently predict. There are several candidates for what this missing piece might be. One is that our understanding of dark matter, the invisible material that dominates the mass of every galaxy and every cluster, may be incomplete in ways that matter for extreme cases. The standard model of cosmology, called lambda cold dark matter, assumes a specific kind of dark matter with specific properties, and it has been remarkably successful at explaining a huge range of observations. But there are known small discrepancies between the model's predictions and various observed phenomena, and it is possible that a modified version of dark matter, one with slightly different clustering behavior on the larger scales, could produce more massive central cluster galaxies more efficiently. Nobody has a compelling alternative that fits all the data yet, but the possibility is open. And every time astronomers observe an extreme central galaxy like IIC 1101, it becomes another data point that the eventual complete theory of dark matter and cluster evolution will have to reproduce. Another candidate for missing physics has to do with the very early universe, and the way galaxies formed in the first billion years after the Big Bang. Recent observations with the James Webb Space Telescope have started to reveal that the first galaxies formed earlier and grew faster than most models predicted. Big, mature-looking galaxies are being found at redshifts that put them in an era when the universe was only a few 100 million years old. An era when standard models expected the first galactic seeds to still be tiny, embryonic, chaotic things. This is one of the most active areas of debate in astronomy right now, and it is directly relevant to IC 1101, because the ancestors of a CD elliptical, the very first proto-galactic seeds that would eventually merge into the central body of the cluster, formed in that same early era. If those seeds were bigger, denser, and more numerous than the standard picture suggested, then the merger tree that led to IC 1101 had a head start. It began with more massive raw material. It could accumulate faster. It could reach the observed final mass with less of a struggle. This is an active area of investigation, and it is exactly the kind of adjustment to the model that might resolve the tension for the largest observed central galaxies. There is also a subtler possibility, related to how efficient the merger process itself really is when you look at it in detail. In a rich cluster center, when a galaxy falls in and gets absorbed, not all of its stars necessarily end up gravitationally bound to the central galaxy afterward. Some fraction get flung out with enough energy to escape entirely, contributing to the intracluster light or even leaving the cluster altogether. And the exact fraction is not something the simulations pin down with perfect confidence. If the real fraction of stars that stay bound after a merger turns out to be somewhat higher than the models assume, then the central galaxy accumulates mass more efficiently per merger, and the top end of the size distribution shifts upward, without requiring anything exotic. This kind of adjustment, small and quiet, may end up being the actual answer. Or maybe not. But it is the sort of small refinement that could add up to explaining why real CD ellipticals sit where they do compared to model predictions. There is one more piece of the puzzle that deserves attention, because it works in the opposite direction from most of the effects we have discussed. So far, we have been talking about what makes the central galaxy grow and where the tension with theory comes from. But there is also a mechanism that actively works against unlimited growth, and it may be part of why the top end of the galaxy size distribution ends where it does, rather than continuing upward without limit. That mechanism is called active galactic nucleus feedback, and it involves the supermassive black hole at the center of the galaxy. When gas falls onto that central black hole, it does not simply disappear quietly. It heats up as it spirals inward, forming an incredibly bright accretion disk, and a fraction of the energy released gets channeled into powerful jets and winds that blast outward from the region around the black hole at nearly the speed of light. Those jets can extend for hundreds of thousands of light years, dumping enormous amounts of energy into the gas surrounding the galaxy. And what that energy does, more than anything else, is heat the surrounding gas up so much that it cannot cool and collapse to form new stars. It also pushes gas outward, expelling it from the galaxy or preventing it from ever falling in. In other words, the black hole regulates the growth of its own host galaxy. If too much gas starts flowing in, the black hole feeds on some of it, produces a jet, blows the rest away, and the growth pauses. It is a self-regulating loop. For a galaxy like IC1101, this feedback is extremely important. Its central black hole is one of the largest ever measured, weighing in at tens of billions of solar masses. And the jets it can produce, when it is actively accreting, are among the most powerful energy releases in the universe. Those jets can prevent gas in the intracluster medium from cooling and falling onto the central galaxy, which would otherwise be a significant additional source of growth. In the absence of that feedback, cool gas would rain down onto IC1101 continuously, forming new stars and adding mass at a much higher rate than we observe. Instead, the black hole keeps the gas hot, keeps it from settling, keeps the star formation rate low, and effectively caps the growth. This is one of the reasons that the central galaxies of clusters, despite sitting at the bottom of the deepest gravitational wells and constantly being fed by mergers, do not grow without limit. The black hole is standing guard, so to speak, blasting the surrounding gas back out as fast as it tries to fall in. And any complete theory of how IC1101 got to be exactly the size it is has to account for this feedback carefully, because it is one of the main brakes on the whole process. I want to be clear about what all of this means, because I do not want to leave you with the impression that scientists are completely stumped, or that a C1101 represents a crisis in our understanding of galaxies. It does not. The general framework of hierarchical merging is not in doubt. The specific mechanism we walked through in detail, the slow accumulation of galaxies at cluster centers through dynamical friction and mergers, is well established and well supported. What is being actively debated and refined is the quantitative fit at the extreme end of the distribution. That is a normal scientific situation. Every good theory has a boundary where it starts to strain, and pushing on that boundary is how we discover the refinements and additions that make the theory better over time. IC1101 and the handful of other supergiant central galaxies like it are stress testing our understanding of galaxy formation right now. They are helping researchers figure out which refinements matter and which do not. And in the process, they are teaching us something about how the universe assembles its largest structures over the longest time scales. Now let me pull back from the technical picture and try to say what all of this actually means, because I think this is where the story gets its emotional weight. Because when we ask why nothing should be this big, we are not really asking a purely technical question about models and simulations. We are asking something deeper. We are asking why a universe with certain properties, evolving under certain laws, ends up producing objects that sit so close to the edge of what those laws seem to allow. Why does the universe have a top end that is exactly where we find it? Why is IC1101 and objects like it positioned right at the boundary between just barely explicable and genuinely surprising? There is something almost aesthetic about this. Something that suggests the universe operates on scales and timescales that are finely balanced, that leave room for extreme outcomes, but only just. That reward patience and location with growth so extreme, it strains the very theories we use to describe it. That is not a coincidence in some cosmic design sense. It is a consequence of how growth in nature works. Anything that grows by accumulation over long times in a favorable environment will tend to end up at the top end of what its environment can support. The tallest tree in a forest sits right at the limit of what soil, water, sunlight, and wood physics allow. The oldest whale, the deepest coral reef, the largest crystal ever found, the tallest mountain, all of these push against the limits of their generating processes. And I, C1101, in its own vastly larger domain, is doing the same thing. It is what happens when you take a physical process and let it run for as long as physically possible in the most favorable location possible. What you get is an object that is not violating the rules, but is doing everything the rules allow and pushing right up against the ceiling. And there is something quietly haunting about that ceiling. Because remember what I, C1101, actually is? Remember what we said about the halo. That massive, faint, extended envelope of stars that stretches out for hundreds of thousands or millions of light years around the central body is not just a size measurement, it is a memory. Every star in that envelope came from somewhere. Every star was once part of another galaxy, another proto-galaxy, another independent object with its own history and its own set of orbits, and its own potential for life-bearing planets, and its own quiet, distant era of existence before it drifted into the wrong gravitational well. And now, all of those histories, all of those individual galactic lifetimes, all of those countless stars are gathered together into a single object. One galaxy. 100 galaxies worth of contents, folded together into one gravitationally bound structure, sitting at the bottom of one very deep well, glowing faintly with the accumulated light of every conquest. If you were somehow born on a planet orbiting a star in the extended envelope of IC 1101, and if you managed to look up through some telescope powerful enough to trace back the history of the stars around you, you would see that you are not standing on the ruins of one civilization. You are standing on the ruins of an entire era of the universe. The stars beside you would have come from dozens of different original galaxies. The star of the neighboring solar system might have formed 12 billion years ago in some small proto-galaxy that fell in early and was digested completely by 2 billion years after the Big Bang. The star on the other side might have formed 9 billion years ago in a substantial spiral that spiraled inward more recently. Every star in your sky would carry a different genealogy. They would not share an origin. They would only share a destination. That is what a CD halo actually is when you think about it that way. It is not a single population. It is a mixed archive of everything that ever lived nearby and lost its independence. And this is where the awe I want you to end with comes from. Because IC 1101 has been doing this since the young universe first started producing galaxies at all. It started as a small seed in the young universe, one clump of matter among many, in a region that happened to be at the deepest local point of the growing gravitational potential. And from that point onward, it has been feeding. Slowly at first, then faster as more galaxies formed nearby and started to spiral in, then slower again as the universe expanded and the local supply of merger targets thinned out. But always, in every era of cosmic history, it has been growing. Every galaxy that ever came within reach eventually got pulled in. Every population of stars that ever formed in a neighbor was eventually absorbed. The universe has been running this experiment for over 13 billion years, and the answer, the running total, the current state of the object we are looking at is IC 1101. This is what the universe produces when the universe is allowed to concentrate matter without interruption at a single location for nearly its entire lifetime. And the last thing I want to say is that IC 1101 is not finished. That is the piece that stays with me the most, and I want it to stay with you. This is not a dead object. This is not a fossil. This is a currently active gravitational engine, still pulling in galaxies from the surrounding cluster, still absorbing whatever comes too close, still slowly growing at a rate that is small compared to its early years, but that has not gone to zero. In 1 billion years, it will be a little bit bigger than it is today. In 10 billion years, if the universe holds together in a way that allows the cluster to remain gravitationally bound, it will be substantially bigger. The mergers that are happening in Able 2029 right now, the galaxies whose orbits are decaying under dynamical friction as we speak, will eventually contribute their contents to the central object, and the central object will keep going. Not because it wants to, not because there is any intention behind it, but because gravity, given time and a favorable location, does not stop. It never stops. It works patiently, silently, across timescales that dwarf everything we would normally consider long, and it produces things like this. So when we ask why nothing should be this big, and when we look at the tension in our models, and the caveats about the measurements, and the honest scientific debate about what fraction of the halo really belongs to the central galaxy, we should not lose sight of the underlying fact. The fact is that gravity, over billions of years, at the center of a rich cluster, builds monsters. It cannot help itself. The mechanism is inevitable. The only variables are how big, and how fast, and how much the surrounding environment cooperates. And C1101 is what gravity built when everything cooperated. When the location was ideal, when the merger supply was rich, when the time available was the full lifetime of the universe. It sits there, 1 billion light years away, in the middle of its cluster, silent and ancient and enormous, a physical object that sits precisely at the boundary of what our theories predict is possible, not violating the rules, not breaking the physics, just doing everything the rules allow, everywhere the rules allow it, for as long as the rules have been in effect. That is the object we have been talking about. That is what is really out there. Not a puzzle to be solved, but a demonstration of what happens when you give the universe an unlimited amount of time and one perfect address, and then walk away and let it work. Thank you for staying with me through this. If you enjoyed traveling to the top end of the galactic size distribution, a like or subscribe genuinely helps this channel keep exploring places like this. And the next time you look up at the night sky and see the faint band of the Milky Way arching over your head, remember, somewhere more than 1 billion light years away, sitting quietly at the bottom of the deepest local gravitational well, an object is drifting through the dark with every galaxy it ever ate, still glowing faintly inside it. And it is still eating. Good night.